Hey, physics! Welcome to another week of love and joy and math. And we are here looking at universal gravitation. And this is a concept that's going to be with you for a long time, so get comfortable with it. Universal gravitation, we're looking at why are you not currently floating? And why, when you cry, do your tears hit the floor? Yes, folks, gravity. It's a wonderful thing. And we are going to be talking today about some of the people involved in discovering it. Certainly not everybody. This isn't a biography of science class, but we're going to hit a couple of the humans that were involved in getting us there to the idea, and then we're going to spend some time in the math. So not actually a whole lot to do here today, but to just introduce this concept to you. So early concepts of the solar system, which is where gravity was first discovered, were geocentric, and Earth at the middle. And that came from some misunderstanding of Scripture. Some things like in the scriptures where it says God has set the earth upon its foundations and it shall not be moved. That doesn't have to mean, according to the grammar, that the earth is at the middle of everything. What God is getting there, what the point of that scripture is not a scientific principle, but rather a theological one, that what God has done will endure. And various other scriptures that, when you kind of squint at them, seem to look like the earth is at the middle of the solar system. So people read that at face value and believed that the Earth was at the center of the solar system. They were wrong, and that isn't the point of those passages. But anyway, they had this concept for a long time. Aristotle also taught it, and not because of his reading of Scripture, just because when you stand around, you don't experience the Earth's motion. You don't feel it happening, and so he thought that the Earth was at the center too. So Aristotle had a piece in it. Misunderstanding Scripture had a piece in it, and it wasn't until around the 1500s, 1300s that people started to question that, and the real proof didn't come until much later. So, geocentric, Earth at the center. The truth is that the solar system is heliocentric, with the sun at the center. That was first proposed in a provable way by Nicolaus Copernicus. Galileo thought so as well. He later recanted and he had no proof. And so Galileo was a little earlier. Copernicus had the math to back it up. So Copernicus said that the Earth was not the center of the universe and it went around the sun. And then a couple of years after his initial statement, all of the mathematical proof was done by Johannes Kepler. And Kepler did most of the math that proves that the Earth goes around the sun. As a matter of fact, he came up with several what we call laws of planetary motion. We'll get to those in just a second here. So just some pictures of what people used to think, with the Earth at the middle, the moon as our nearest satellite, and then Mercury and Venus, and then the sun, and then Mars, and then, yeah, anyway, it got confusing. So the planets going around the Earth and the sun going around the Earth. But that doesn't quite line up with observations because if you ever watched planets go across the sky from night to night to night, they don't just travel in a straight line. They like go forward and they go back and they go forward and they go back. And that's because we're rotating along with them. And so our perception of their motion is not purely linear. And so in order to explain that, certain people said, oh, well, there's these epicycles. See, we're in the middle. The moon goes around us. And then Venus actually rotates around an unknown center of rotation. And that center of rotation rotates around us. So it's like spiraling loop-de-loop-de-looping. And all these other planets are doing that too. So you get this like forward and then back and then forward and then back and then forward, expression of how the motion happens. Really complicated. Nobody could figure out why these things are rotating around something else that they can't see. And so this was ugly, but did in fact predict where you could find the planets at any given night in the sky. But we didn't know why. And so along came Nicolaus Copernicus, and he did some of the math and explained the observations better with a circular rotation around the sun. But his pinpointing of where the planets were was actually not perfect, because he assumed that it was a perfect circle of rotation, and it was not, in fact, a perfect circle of rotation. Johannes Kepler, a little while later, did all of the hard math and proved with great precision that it was, in fact, an elliptical orbit around the sun. And so we have Johannes Kepler's laws of planetary motion, okay? And you do need to know these. So the first law here, that the solar system's orbits are ellipses, not circles, and that the sun sits at one focus of the ellipsis. And if you don't remember from algebra what an ellipsis is, it's like a circle, but it's been stretched in one dimension, and there are two centers. There's the two foci is what we call them. And the sun sits at one and nothing is at the other. The second law of planetary motion is that the position vector of a planet travels through equal areas and equal times if the vector is drawn from the sun. What? Pictures will help. Trust me, you'll understand in just one moment here. And the third law is that there is a constant ratio between the time it takes a planet to orbit, which we're going to use as capital T, and the average radius from the sun, which we're going to use as capital R. Okay? So, and if you square the period and cube the radius, you get this constant called K. What's the value of K? Doesn't matter. Just know that there is always the same relationship between the square of the rotational period and the cube of the average radius of rotation. So pictures will help. Pictures to the rescue. Here we go. This first one up at the top is going to help you understand the first two laws. So the orbit is in fact an ellipsis, okay, not a circle. And the sun sits at one focus of the ellipsis. There is nothing at the other focus of the ellipsis, okay? The sun sits here. So that's the first law. It's an ellipsis, not a circle. The second law is that the vector position sweeps out equal areas in equal amounts of time. So if you just look here, in this amount of time, in time t, a planet will go from here to here. It actually traveled a greater degree of arc than the same amount of time here or here. Same amount of time, greater degree of arc. Is the planet going faster? Yes, right here. Why then, how can we predict how fast it's going in one particular time? Well, we have to stop looking at degrees of arc, and we have to start looking at the area that it swept out. So the vector went from here to here. And calculus will let you calculate the area of this odd shape, okay? You're not in calculus right now. That's okay. Take our word for it. The volume here is the same as the volume here, and is the same as the volume here. And so these volumes are equal, and the planet's travel sweeps out equal, I've been saying volume, equal area of these ellipses in equal amounts of time. Okay, and then here's that rotation, or the time period and radius rotation relationship. If you take the average distance that Mercury orbits the sun, so this distance and this distance averaged, okay, and you square the rotational period and you cube the average radius, it plots here on the graph, and you'll notice that all of the planets plot along the same line. They're all data points on the same line. So given any object with an average radius from the sun, we could predict how long it would take to rotate. Okay, so that's the third law. Those are Kepler's laws of planetary motion. You won't have to do a whole lot of math with that, so that's okay. Now we get to Isaac Newton, who is really Mr. Gravity. Johannes Kepler and the others calculated where things would be and explained why, but didn't know about gravity. The force that applied, the centripetal force, was unknown to them. Isaac Newton was the one who discovered and described gravity. Okay, so Newton's work was on the invisible attraction between the sun and the planets. He was the first one to coin the term gravity, and it actually comes from the Latin word for fatness. So the bigger something is, the more impact it has, is the idea here. So yes, the fatness of things. And he determined from Kepler's work that the strength of gravity had to do with the distance of separation, and that's that Kepler's third law, that the amount of pull has to do with how far apart these two things are. He did his own experimentation to prove to himself that the masses of the two objects that we're talking about also play a role. Kepler didn't take that into account. And so when you put together that mass and radius of separation goes into the force of gravity, you get this equation, okay? The force of gravity is equal to some constant times the masses of the two objects you're looking at. And in your book, it just says capital M, lowercase m. I didn't think that was as clear. I had memorized it always as M1, M2. I think that's easier to conceptualize, whichever way works for you. But you have the masses of the two objects, okay, times the gravitational constant divided by the square of their radius of separation. So the value for the gravitational constant, G, was unknown for 200 years after Newton. He knew that it was there, he just didn't know what it was. We now understand that the gravitational constant is 6.674 times 10 to the negative 11th Newton meters divided by kilograms squared. That is an ugly unit, but basically what it does is it reduces all of this to an answer that is newtons. Okay, so don't get too tied up in the unit. Know the number, 6.674 times 10 to the negative 11. Okay. Gravity is always an attractive force. There's no such thing today as anti-gravity. Science fiction talks about that. We have not discovered any such force. Okay. Radius of separation is always measured from the center of mass. And so we'll see in an example here in a minute. You don't measure from the surface of the Earth. You measure from the center of the Earth. And that's what gives us the right answers. So here we go. Math with gravity. Yay! What is the force of gravity for this astronaut, who, with his gear on, has a mass of 150.2 kilograms, floating 405 kilometers above the surface of the Earth? If the Earth has a mass of 5.972 times 10 to the 24th kilograms, which actually does, that's a huge number, and a radius of 6,371 kilometers, which is also accurate. So here's the radius of the Earth, here's the mass of the Earth, here's the mass of the dude, here's his altitude. We'll need all of this. Okay, first we need to know what's the radius of his separation from the center of mass of the Earth, which would be his altitude plus the radius of the Earth, right? He's this far above the center of mass of the Earth. We don't care about his altitude above ground. We care about his altitude from the center of mass. Okay, so we have this number now as the number of meters, because that equation requires meters. And this number was kilometers, so I need meters. So I have to convert the units up. Okay, so force of gravity is G times M1 times M2 divided by R squared. G, I'm going to leave it just like that for a while, just G. 150.2 kilograms times 5.972. That should, oh yeah, times 10 to the 24th kilograms. This is the mass of the Earth. This is the mass of the dude in his gear. Okay, mass of dude, mass of Earth. This is the radius of separation from the center of mass of the planet. And so then I have to square that. So there's that number squared. Okay? And now I multiply the mass of the Earth times the mass of the guy. Notice the mass of the Earth is a lot bigger. It's not going to actually change all that much when we multiply it by the force of the guy. So we have the product there of the masses of the Earth times the mass of the guy. And then this is, again, the square of their distance of separation. Now notice I have kilograms squared, I have meters squared in my units here, and notice that I have meters and kilograms squared, but in the opposite position. Meters are above kilograms here, kilograms are above meters. So my unit for G is going to undo all of that nasty and just reduce me down to newtons, which is why this unit is what it is. Okay, so I have grams, I have my constant of G. When I divide this number by this number, I get this big number, way too many digits. We'll fix that in a minute. And then I need to multiply that times G. G is this number. And when I multiply them together, I get this number. And I have, in fact, 4 significant digits, 3 significant digits, 5 significant digits, and 4 significant digits. 3 is my limiter, so I should express this answer. I didn't on the slide, I just realized, but I should express this answer as 130. I should express it as 1.30 times 10 to the second times 10 to the third. I can do this in my head. Newtons, there you go. I should only express that in 3 significant digits. So there you go. Except for the little rounding thing at the end, that is in fact how you work gravity problems, okay? If you have any questions, please post them in the comments field below, and I will see you tomorrow in class. God bless you. Have a great evening.